In this video, we present our work, Self-Supervised Environment Synthesis. It is common that a pre-trained deep prior policy, for example here, a robot in a simulation, being deployed in a completely different environment, for example here, in parks, factories, or household. To solve this adaptation problem, we introduce our method, Self-Supervised Environment Synthesis, or SES. Assume we have an original policy, for example, trained in the simulation. We want to adapt it to a different real-world environment. The core idea is to use limited navigation experiences during the deployment to reconstruct the navigation environments in the simulation, and by training on them, the original policy's performance could be improved in the real world. By this means, SES will ease the large amount of data required to train the policy directly in the real world. More specifically, from the navigation experiences, SES performs trajectory segmentation that segments trajectories into small navigation scenarios. Then we identify the challenging scenarios out of them to facilitate adaptation. Next, SES synthesizes environments based on the challenging scenarios that are more representative and diverse than the raw challenging scenarios. Finally, by training on these synthesized environments, the performance of the original policy can be improved. We deploy an original policy in habitat environments. During the deployment, the robot will easily get stuck at some challenging scenarios. Habitat domain representation and trajectory segmentation. To synthesize the environment, we only select scenarios where the robot gets stuck and get such a representation of all the challenging scenarios. Then we use GAN to synthesize the environment. We generate such a set of training environment from all the challenging scenarios. After training on the generated environment, we deploy the policy in one of the habitat environments. In the upper left, you can see the agent that was trained on the environments generated by a GAN. The top right shows the agent trained on environment that randomly sampled from the challenging scenarios. The policies are both learned using the same algorithm which we specify in the paper. The lower left shows the original policy and the lower right shows DWA, a classical navigation stack with default hyperparameters. As you can see, GAN finishes the navigation first, then the random follows. Both original policy and DWA suffers from many recovery behaviors and navigate very slowly. Physical experiments. This two video shows the SES policy and the original policy deployed in the challenging scenario 1. As we can see, SES policy could navigate much faster, while the original policy suffers from many recovery behaviors. Similar tendency is also shown in the challenging scenario 2. Thanks for watching this video.